The next section, it becomes getting more complicated. So it's generalized from the Legendre equation, or you can say Legendre equation is a special case of this equation, because we get this equation first from the separable solution, either the Laplace equation or the Helmholtz equation and all that. And so that equation is now 15.68. Let's write it down. The function of the differential equation is p, is second derivative, d pi x, and then you have this lambda. In general, you put this general eigenvalue here, and m squared. The extra term is this m squared. P function x. Right. So when m is 0, then we get back to the Legendre equation. Now adding for this term for non-zero m, then the complication is that this is one over 1 minus x squared factor here, so that makes the solution more complicated, and in particular, the solution will be no longer the simple power series or polynomial. And so, but one thing to solve it is it's not, although it's not a polynomial, it becomes a factor non-power series factor and multiplied by a polynomial. So that is the idea, and that is simplified. And this lambda is coming from requiring the solution to be regular, especially on the axis, or theta is 0 or pi, or x equals to plus or minus 1. Right, and that will fix this lambda to be L times L plus 1. So later, we already learned that from the Legendre equation. We have this, or in our notation, in the notation of the textbook, n times n plus 1, n is 0, 1, 2, 3. So later on, we'll actually do that. And so this object will now, you impose that, this will carry over to this equation also. So this P actually have two label. So you need to label it with this N and then this M. So later on, this P will be P N M, right? And then we'll figure out there's a restriction of M with respect to N also. We'll get to that almost immediately. Right. So, but this equation, we just sometimes we're ignoring this notation N and M just for simplification in writing. All right, and now the first thing to simplify this equation is do a transformation so that we get the equation that looks nicer. Is in particular this inverse of this function. I mean, this function is more difficult to make the whole thing. The solution is not the polynomial. If we get rid of that, then hopefully we'll get a solution that is again polynomial. And so the transformation is suggested by this notation. P is 1 minus x squared m over 2 power and then another p, but different different way to write a p. This is script p. Okay, this is regular p. Okay, so if we do this transformation, we can work this out, but it might take some time. But it's straightforward. So the textbook has a few lines of showing that. I actually had this all these details in my video. So and you probably all know how to do that, right? Because it's just involving taking derivatives, the first derivative and second derivative of this one, and then work out the distribution of the derivative over these two factors, and then substitute it back to here, and then finally you see that every term will have this proportional to this factor, so you can get rid of this factor and get a solution for the script p only, and that that equation is simpler than this one. So after all that, so assuming you do that, work this out, then the equation is the next one, 15.72. So 1 minus x squared with p double pi minus 2x m plus 1 with p pi lambda minus m. So that equals 0. Okay, so from this to this is just this transformation. You work it, so you get this one. Work out the transformation. Right. Now this equation is easier than this one because you get rid of this 1 minus x squared factor. So if lambda is just the same as this one, then all these coefficients will be regular, right? So the solution will be similar to the Legendre equation. Remember the Legendre equation just without this term. Without this term, is set m equals to 0, or both are setting m equals to 0, right? Then you get the Legendre equation, right? And now the solution for this is following the same way. You can first look for a series solution. Just the usual way to do a series solution, and then the solution will, the convergence of the series solution will require that the series to truncate, because if we include all terms, then the function will be divergent at x equals to plus or minus 1. Right, so it's just following the same object as the Legendre equation. So the boundary term is singular if the series doesn't truncate. You can find a solution that is just an infinite series, but that solution will be singular on the boundary points, right? So that the truncation required the same the actually required the truncation required lambda equals to like n times n plus 1, right? And then the summation of the series will be sum over j up to, right? So you look for a solution like just following the same the usual ideas of j from 0 to infinity, a sub j x to the j plus the whatever s. I think your text is using k in this one. The k is determined by the initial condition, and then after you substitute this, and then you can find out the condition for k. As for this one, you have k is 0 or 1, and but anyway, truncation require two factor, two conditions. One is the lambda is given by this same n times n plus 1 value, similar, I mean, the same as the Legendre equation. And then this summation will be sum over j to m. I think it's j to, because it's j is sum over to if j is L times L minus m, then the next order or next a sub j plus 2 will be 0. So you truncate at the L minus m. So finally, this is L minus m. Right? And that we require this. That's the second condition for the truncation, right? And right. So that's that you satisfy if lambda the eigenvalue is like that, and you the sum is only over up to L minus m, then that's the solution. That becomes a polynomial, okay? And this is called associated Legendre polynomial, okay? And now yeah, n is just the same. So I wrote the L, yeah. And because the textbook going back and forth, so in this discussion is using L back to L, right? Yeah, in this section back to L. So, where did it start going back to L? I mean, the first section obviously going from N. Now it's going to L. Yeah, well, in the last section is still N up to 15.63. I guess somewhere along the line is this anyway. It says most people would call it L, but the textbook chose to call it N. It's just the same thing. Right, but anyway, now this is the first, just the first transformation, and show that this P is given by this equation, the solution of this equation, and then it's a truncated series is a polynomial, and then the truncation is given by the same n, or like going back to L. And now the idea is you can write down at least one kind of solution of this one by the solution of the Legendre polynomial, the Legendre polynomial. The equation for Legendre polynomial just setting m to 0, so 1 minus square. Now, writing out explicitly in your textbook now, going back to L. Let's going back to L. So L double pi minus 2x dl. This is not script. This is just the Legendre polynomial, the usual Legendre polynomial. And then plus L times L plus 1 dl equals to 0. This is the Legendre equation and satisfied by this PL for a given L value, right? And then the idea you can show that a solution to this equation for the script p is a repeated derivative of this PL and depends on m. So it's dx, the m terms, m derivative of x and of this piece of L. Okay, piece of L is a function of x. Okay, so now this object, after you take the m derivative of this Legendre polynomial, will satisfy this equation, associate Legendre. This is this what this. We have too many equations. At least this is called the associate Legendre polynomial because I mean after you normalize it, but that's the polynomial solution. But this you show that this satisfies this one, and to show that again is a little bit of work. You basically substitute this into here. So script p equals to u. You need to do the pi. You need to do the derivative of this one, and then the derivative of this one, right? And so it's not too. I mean, it's just a few lines of work. Then supposedly you get to show that this satisfies this equation, and so I again I have a video to show that, but probably shouldn't spend the time here to actually prove that. But if you just substitute this into this the script p and change this to now back to L times L plus 1, right? It's L times L plus 1. Then you can show that this satisfies this equation. Now the important thing is that this solution exists only for m less or equals to L, right? Because we already talked about that piece of L, the highest power of x is x to the power L, right? Previously we called it piece of n, the highest order is higher power x to the power n. Now for this one, the highest power is x to the L power. Now you take m derivative. If m is greater than L, obviously you make it 0. Right? You take more derivative than your power, you make it 0. So the highest m will be less or equals to L. So m is required to be less than L. Right. All right. And another thing is this is defined for positive m, right? So this script p, if you substitute script p, this in the script p, and then usually we normalize that. And the normalization is very simple. It's just the script p now depends on L and m. It's just with this negative m power dx m power Lx. Okay, and that is defined as your associate Legendre polynomial. Okay, and now with this, then we can go back to this object because we introduced the script p by this p that satisfies the original associate Legendre equation, right? And so assuming that we already accepted that this is a solution for this equation. So and this equation is coming from this equation after you do this transformation. So this one multiplied by this factor will satisfy this equation. Okay, so that's the idea. All right, so we can now substitute this one into back to here and write down the associated agenda function. All this. Now for different m and different l, the the definition is with the factor multiplied by here, and then you have this dx m m derivative of this pl. And then we define this as your pl and m. So this is the Legendre associated Legendre function, because this is not a polynomial, because after you multiply by this factor, it's no longer a polynomial. It's a polynomial for this part and then multiply by another function. Okay. All right. So far it's required the m is less or equals to L. And up to here, m is still the positive, right? And the next step is to introduce a negative m, the negative value of m in the definition of the associated Legendre function, because it's actually defined for m is not just this. We'll finally extend it to m less than L and greater than minus L. So all the way to m will take the value of minus L plus 1, and so on, including 0. M is 0, just get back to the cylindrical symmetric case, the Legendre polynomial. You have this actually minus 1, 1, all the way to L minus 1 and L. Okay. M is taking all this value. Okay, and now in order to extend all this negative value, we use the Rodriguez formula, and the Rodriguez formula is have a normalization. You go back to the definition of the Rodriguez formula for the Legendre polynomial. So P, going back to equation 15.30, the P sub L. Now going back to the L, using L as your variable, to the power L factorial dx to the L derivative, and then x squared minus 1 to L power. Okay, so that's the Rodriguez formula. Right, so now you put it back to this definition. Which is here. Let's substitute this into here, right? So P L M, okay, given by minus 1 to the M power to L to the power L factorial minus x squared M over 2. These are coming from the Rodriguez formula. And then now combine all the derivative, becomes this is L plus M. And then operate on x squared minus 1 L power. All right. So that is using the Rodriguez formula, the definition of this PLM. Now with this, you can extend the negative m, right? Because you already take the L the derivative. If m is negative, then this total L plus m, if total L plus m is still positive, then the derivative still exists, right? And I mean, it's still defined. If you take negative, the derivative of obviously is not defined. But if you take the derivative with L plus m, so require this L plus m is greater or equal to 0, or m is greater than minus L. So that's the second condition. So the first condition, when we derive this the script p solution, which basically this part, we require the m is less than L, because that's how you take the m derivative of PL, which is not exists if you are you take more derivative than the highest power. You call this condition. And now after you extend it using the Rodriguez formula, because that PL already has the L derivative of this factor, then you can extend L after you combine the derivative is total number of derivative L plus m. So as long as L plus m is greater than 0, greater or equal to 0, then it's still defined. So you can define your associated Legendre function even from minus m. So with that, so the total condition for the m number satisfy this equation. It's okay. So that's one of the restriction of the associated Legendre function, which is important when you need to sum how many mode do you want to sum, how many terms do you want to sum, then that's the restriction you sum over m. And remember, this m is associated with the cylindrical, the azimuthal part. So m is associated either the im, the same m, right? The same m. And if we use the exponential function for the azimuthal part, and m takes any integer, so positive or negative integer. But after you combine with the theta part of the solution, now you restrict your the choice of either the im5 by this L. For a given L, then this m is not arbitrary. It's just summing over the range, this range. Okay, so the azimuthal part depends on the theta part in this sense. Okay, so that's the important limit. Okay, and now the next equation is a little bit difficult to choose. I think this is an exercise which we won't go through. I'll probably post that that question and solution. That is my solution for this one. So after you extend it to minus m, the two m and minus m actually turns out to be not dependent, not independent, but they are not equals or simply related to each other. Actually, they have this proportionality constant turns out to be non-trivial, but sometimes that constant is important, and especially when we talk about this the orthogonal condition. Usually we talk about orthogonal condition not just for associated Legendre function, which you can do. You can do that discussion, but usually we combine this one with the azimuth part and combine and call it YLM, and then do the orthogonal condition using spherical harmonics. but the definition of spherical harmonic would depends on the normalization of this PLM also, and so that's this constant becomes important. So it's actually -1 to the m power L minus m factorial L plus m factorial and Lm x. Okay, it turns out to be the dependent, the two actually dependent. It doesn't look obvious because remember you go back to this definition. So PLM required you have L plus M now, assuming M is positive. It doesn't matter, even if you change M is negative, then you see that this is symmetric. You treat it like negative, this become positive. But then all these terms will reverse. This become positive, become negative. It's just divided the whole factor to the other side with the same equation. Okay, so that's this equation is symmetric between positive and negative m. Anyway, if you assume this for this definition, M is greater than 0, then this term, this factor will be taking the L plus m derivative of this factor, x squared plus -1 to the L power, which would taking more derivative than just L, assuming M is not 0, right? And then for this guy, then you're taking L minus this is minus M, right? So this is negative. Then you L minus M derivative, so you're taking less number of derivative than L, right? And of the same factor, and why you get this relationship is not obvious. One way to do it is just try a few times. Try some lower value of the stuff. L is 0, 1 or 2. That's a little different thing. If L is 0, M must be 0 because of this restriction. For L is 1, then M can be 1, 0, and -1. And L equals 2, you have 2, 1, 0, -1, -2. Right? You can check a few cases and convince yourself that this is satisfied. It's just take direct derivative of the space on this definition and show that they actually satisfying the same this equation. Whether you're picking more derivative than L or less derivative of L, finally they are actually proportional to each other. And one idea is that you multiply this one with this function. You have M. So positive M, you multiply 1 minus x squared, the positive power. Sometimes it depends on M is odd and integers, or odd. So even number is just becomes a power series of x. For odd one, it's just inverse of that. I mean, it's half integer, so it becomes square root function. But the difference between positive m and negative m is negative m is divided by this thing. But then after everything, after you take the enough derivative, you see that they actually, after some cancellation, you show that they are actually the same. Whether you're taking L plus m derivative or L minus m derivative after you multiply by a corresponding factor, it turns out to be proportional to each other with this proportionality constant. But anyway, that's just a nice property, and that you need to, because when we're expanding function, we need to realize that whether they are linear dependent or independent, so that affect you're doing expansion. If you just use an associated Legendre function to do expansion, then obviously you don't sum over all the m, because that becomes redundant for positive m and negative m, right? But the spherical harmonics becomes useful in the sense that it's multiplied this object to either im phi, and then im phi is independent, so e to the I phi, m phi, and e to the minus im phi. They're linearly independent. So if you multiply PLM, you multiply PLM with e to the im phi, then this the positive and negative m becomes independent again, because even if the associated Legendre function part is dependent, but you multiply by this the exponential function. That the exponential function part is independent, so the total is independent. Okay, so that becomes make it simple and easy to use. So this will be proportional to what we call the YLM. It depends on the occasion. Some people put the m in the subscript also, but the other people will differentiate between whether you put m in the superscript or subscript, and they will be two different objects, maybe two different kind of normalization. But anyway, one more thing is just don't confuse all this m. Superscript is not power. That's actually elementary problem. So all this in the superscript thing, if m is not the Legendre polynomial to the m power, not like that. It's just conventional notation is putting it in the superscript, so that need to be a little careful. All right. Now the next set of discussion is the recurrence formula. Now, because of all these objects have two variable or two label L and M, then the recurrence formula becomes more complicated because you can increase or decrease M or increase or decrease L. So you actually have more recurrence formula than just the Legendre polynomial, which you have two of them. And the recurrence formula for this PLN actually coming from the script P. Right, so you first work on the script P recurrence formula first, then using this definition, then extended that to the recurrence formula for the associated Legendre function. The forms are different. Obviously, the forms are different, and because you have this factor, and sometimes this factor will enter the recurrence formula also for BLM, so that make it complicated. But anyway, I think we'll talk about that next time. But any question up to here? I went through it quite just basically outlining the all this argument, but the details in the derivation probably, if you would like, or when you have more time, you can go back to my video and then I fill out all the details in the video. Okay, so